need to slowly begin our next topic. I think I uploaded some videos. Have you guys had a chance to look at them last Monday? The concept of coordination complexes. It's a very important concept. The topic is extremely critical for the advancement of science. As we go through the examples, you will know how important this chemistry is. Of course, we already talked inorganic chemistry is extremely critical for industry. And this is even more critical, the coordination complexes. In fact, this area won several Nobel Prizes for the discovery of the coordination compounds, starting with Werner in 1913. We're talking about a long time ago. All right. Again, I'll make a final request to all of you that those of you who are comfortable turning your video on, please do so to make our experience as close as possible to in person. The only exceptions are when you are not comfortable showing your backgrounds. Apparently, I was told that you can also hide your background in Zoom by selecting a virtual background, so you don't have to be embarrassed about your surroundings, because you can always create a fake background that should make you comfortable joining the video. All right. Again, I cannot force you, but I only encourage you to turn it on if you are in a comfortable situation. With that, let me now take any questions you may have on the coordination complexes. Anything that's not making sense. Gurveer, you can start recording if you can, please.
I did.
Okay, thank you. Excellent. Any questions so far? You all understand how to name a coordination complex, names of the ligands. There are technically 4 different aspects of coordination complexes that you will be responsible to know. One is understanding the geometry of the coordination complexes. The other thing is understanding the isomerism of coordination complexes. The third thing is naming the coordination complexes, because they follow a very strict regiment of naming. You can't randomly name a coordination complex. There are certain rules for nomenclature, just like organic compounds have a nomenclature, and inorganic binary compounds have a nomenclature system, and coordination complexes have yet another different nomenclature system. I think we talked about, I uploaded all the videos, in fact, covering all these aspects. Finally, you will be responsible to know what I call the 18 electron rule. Just like the octet rule applied to covalent compounds, we use the 18 and 16 electron rules to write down the electronic stability of the coordination complexes. Okay. Just to give you some ideas about the applications of the coordination complexes, the most visible application of coordination complex is the chemotherapeutic drug cisplatin. You heard of that, right? Platinum-based cancer drugs. That's a coordination complex. Contains 2 chlorine ligands and 2 amine ligands. Amine is basically an H3. That is one of the most potent therapeutic that is available for treating cancer today. In fact, there are 3 or 4 different variations of the same cisplatin now being approved by FDA for treatment of deadly cancers. Okay, that is from the therapeutic applications. And coordination complexes are also used in treating toxic metal poisoning. For example, if you have accidentally ingested mercury, for example, or lead, these we know are heavy metal poisoning, right? And one way to get rid of those heavy toxic elements in the human body is adding specific ligands that will bind to these metals and take them away from the stream. I don't know if you heard of this or not. These are called ligation therapies. That is using a ligand to remove the metal. how important it is. Similarly, some of the muscle relaxants, nitrosyl complexes, are used routinely for treatment. So there are a lot of medicinal applications for this particular area of science. In addition to medicinal applications, coordination complexes are also routinely used in industry to make fine chemicals. Like, for example, if you want to make vinegar, right? Vinegar is acetic acid. Anyone knows how it is commercially made? Hmm? We make tons and tons of it, right, every year. There is a coordination complex that makes the life easy. Basically, what you do is you start with methanol and insert a carbonyl group using a rhodium or ruthenium complex, specifically triphenyl phosphines. And they are also used in hydrogenation reactions. Commercially, if you have monounsaturated or polyunsaturated oils, if you want to make fats out of it, you need to do what we call hydrogenation. The hydrogenation is carried out quite efficiently on an inorganic coordination complex. It's amazing, right? A reaction that will take extremely high pressures and high temperatures can be made at very normal conditions, at room temperatures or at ambient pressures, by using these inorganic complexes. Yes, Fatima, question?
Oh no, sorry. My laptop's about to die, so I was trying to plug in the charger.
Okay, all right. Good, okay. No problem. Anytime you have any question. The reason is you will appreciate learning this science and you will have an incentive to master this art if you know where it is being used, as opposed to saying, well, this is something that you need to know. Those of you who will be taking advanced inorganic chemistry next semester, that's in the second sequence of the course, we will teach you all those industrial methods of catalysis using coordination complexes. Okay. So if you go and take up any industrial job, there is no way but to encounter one of these complexes in your routine labs. That's how important this area is. Both medicinal inorganic chemistry as well as fine chemical industry. You must have seen in organic compounds too, right? Organic chemistry. You must have been using some tin-based, lead-based, magnesium-based complexes as catalysts. And these are even more sophisticated catalysts. Wilkinson catalyst. I don't know if you heard of Wilkinson. How many of you have heard of Wilkinson? None. It's amazing, right? Won a Nobel Prize. Jack Halpern and Wilkinson won the Nobel Prize for discovering a coordination complex that does hydrogenation at less than 50 atmospheres pressure and about 40 degrees Celsius, which used to take extremely high temperatures and high pressures. And that was a very dangerous way of making hydrogenation reactions in the past. We're talking about commercial processes, not just lab processes. Okay. Yeah, I mean, you all know about Einstein, and you are pretty much content thinking that there is only one chemist in the entire world, entire universe. Not to take anything away from Einstein. I love Einstein. I admire Einstein. I have tremendous respect for Einstein, but I also have equal respect for others who have contributed to the science. Okay. Anybody on the street will know the name of Einstein. Only inorganic chemists know many other people. I think I have been mentioning the Nobel Prizes as we were going through, right? We're talking about Niels Bohr, Linus Pauling, right? Max Planck, all these guys. So it's important that you have to start appreciating different inventions. And you will start admiring them just like the way you have been admiring Einstein. You'll expand your base. Okay. So inorganic chemistry that way. The first Nobel Prize in medicine, folks, was given in the area of inorganic complexes, antimony complexes. Those days, syphilis used to be a deadly disease. When somebody contacted syphilis, that was almost like a death sentence. But this Nobel Prize discovery changed that, antimony complexes. So not only in the area of chemistry, the area of coordination complexes goes above and beyond the simple inorganic chemistry regime. Okay, so it's important that we need to keep that in mind when you are learning this. This is one of the important, of course, when I talk about any topic in inorganic chemistry, I become very passionate because I see where the applications are. When I see a new discovery, I get thrilled. Just like you get thrilled when you watch a football game. If your favorite team wins, you get excited, right? So I get excited when I see my team of chemists discovering new things. But your excitement watching a football game may be temporary, but my excitement is almost permanent. So that's where I see the analogy. Okay, I'll give you a good idea about how all this started, okay? It all started with a mind-boggling discovery. Okay, we'll start with what we know and slowly walk you into the area of what we don't know, right? We all know, if you can see the board here, can you all see the board, folks?
Yes.
Great, excellent. If I have silver plus ions and chloride ions, what do you expect? If I add silver nitrate to sodium chloride, what do you get? Yes, Fatima?
You just get AgCl, right?
You are absolutely correct. Is AgCl soluble or insoluble?
I think it's insoluble.
You are absolutely correct again. AgCl is one of the most insoluble salts, right? So when you take an aqueous solution of silver nitrate and add an aqueous solution of sodium chloride, you get instantaneous precipitation. In fact, that is a test for chloride qualitatively in qualitative analytical chemistry. This is how you detect the presence of chlorides, and you get silver chloride white precipitate. Okay, so if you look at this, if you have a test tube where you have done this reaction, you will see a white solid inside the bottom of the test tube. That's very well known. That's well known. But that's not the point here. Here is the trick. When I add ammonia, aqueous ammonia, to this, after some time, quite miraculously, the entire solid dissolves. That is not expected. So clearly ammonia is doing something to the silver chloride that makes it dissolve again. What is it doing? Ammonia has no known reactions with either silver or chlorides.
Is it forming a complex with the silver?
You're absolutely correct, Samantha. That's what happens. What happens is when you take silver chloride, solid, and add aqueous ammonia, NH3 liquid, what you make is you make a complex that looks like this. Here, the typical valence of silver is 1+, right? So anytime you combine silver with other anions, the combination is always dictated by the valence of silver that is +1. So if you have chloride, -1, it's always 1-2-1 complex. But here, you're making a complex that appears to violate the valence considerations. In other words, the combination ratio here, silver to ammonia, is way above what is expected from normal valence considerations. And that's exactly what we mean by a coordination complex. These are special class of compounds. So what happens is, as soon as you make this complex, it dissolves in water to give you a cation, which looks like this, AgNH3 twice +1 plus Cl minus aqueous. That is how silver chloride dissolves. So, how exactly are these complexes formed? Is it just always 1 to 2? Is it only silver that makes these complexes, or do other metals form complexes?
Other transition metals.
Transition metals as well as main group metals too. Okay. Apparently, a majority of the metals, both alkali metals, transition metals, and main group metals. Alkali metals are those in groups 1 and 2. Transition metals are from scandium to zinc in the periodic table, and the 3 rows below them. And in the P block metals, like lead, antimony, these are all main group metals because they are in the P block. Bismuth, thallium, right? Selenium, tellurium, these are all different metals that are basically, we call them main group metals. Invariably, there are lots of combinations. So apparently, ammonia is not the only complexing agent. So we use a name to define these functional groups that attach to the metals by name ligand. Some people pronounce this as ligand too. Okay. It's the same thing. Spelling is same, but the way we pronounce may be different. Especially in Eastern Europe, they call that ligand, and we generally call this ligands. Either way. What we now know is we can have a ligand, not just ammonia, but several hundreds of them, as long as they have a pair of electrons to donate. Okay, so for example, if you look at ammonia, we'll start with what we know already. We know ammonia is trigonal pyramidal molecule with a pair of electrons, which can be donated. So on that basis, this can be a ligand. Similarly, if you have water, H2O, this can be also a ligand. Or if I have chloride ion, chloride ion has an octet arrangement like this, and it has a pair of electrons that can be donated. So practically anything that has a pair of electrons to donate can serve as a ligand. Now, the question is, can I have oxygen as a ligand? There's a pair of electrons, right? Yeah. So clearly it can. This ligation property of oxygen is the very basis for your life here. The fact that we are all alive and breathing is because of the ligation capacity of oxygen to bind with heme. So when you breathe in air, the oxygen in the air binds with the iron of the heme or hemoglobin, which carries this oxygen to different parts of the cells and delivers the required oxygen. That binding of oxygen to the hemoglobin is because of the presence of pair of electrons. Same thing with the carbonyls. I have carbonyl, right? This can also bind. So what's the consequence then? Breathing carbon monoxide versus oxygen. You all know, right? Carbon monoxide is a toxin. The toxicity of the carbon monoxide is because the CO or the carbonyl ligand binds preferentially to the heme. Thereby, the heme will lose its ability to transport oxygen, and that leads to death slowly. The same thing happens with cyanide poisoning, CN minus. So when you have cyanide and oxygen, the cyanide binds with the metal or the iron of the heme preferentially and cuts down the supply of oxygen to the cells, causing death. So the toxicity of various elements and the ligands can also be attributed in terms of the coordination complexes we are talking about. There are, of course, some compounds that can never act like a ligand. Can you think of a molecule that has no lone pairs to donate?
What was the, can you repeat the question? I'm sorry.
Can you think of a molecule that has no lone pairs to donate? Because we said for a functional group to be a ligand, it must have a pair of electrons. This is almost like a Lewis base, right? That's the definition of a Lewis base. So all Lewis bases or ligands can, in principle, be ligands. So can you think of a molecule that does not have a lone pair of electrons to donate? So that way we can see why some molecules can never serve as ligands. I mean, you know this. I mean, you just have to connect the dots.
BH3.
BH3 is wonderful. No lone pair of electrons. But it can accept a pair of electrons, right? Because it's an octet deficient molecule. Although it cannot donate, but if there is a ligand nearby, it tries to bind with this. So for example, BH3 will bind with ammonia to make the Lewis acid-base salt, where ammonia serves as a base and BH3 serves as an acid. You're right, BH3 can never donate a pair of electrons. Continuing on the same lines, can you think of some more molecules? Hydrogen can bind. That's an exception. The pair of electrons in the hydrogen-hydrogen bond can be used to bind with metals. So hydrogen, luckily, is very active in terms of its ligation properties. But if you look at molecules which are extremely stable, such as methane, can it serve as a ligand? No. In fact, there are no known complexes of methane. Methane
But
does not bind.
CH3 can though, right?
CH3 can, methyl groups, yes.
Yeah, methyl group.
That can be because this has lone pair of electrons. The charge there tells you the availability of excess electrons on this species, right? So that forms the basis for the complexation with the alkyl complexes, methyl complexes. But methane by itself cannot complex because it has no lone pairs to donate. Okay. All right. So when you look at the ligands, ligands generally are mostly two types. One is anionic ligands, that is ligands that carry a charge. For example, SO4 2 minus, Cl minus, Br minus, I minus, NO3 minus, NO2 minus. Okay, these are all anionic ligands. That means they have a charge. On the other hand, you can also have neutral ligands. Neutral ligands are the molecules which are neutral to begin with, such as oxygen, for example, or NH3 is a neutral ligand. H2O is a neutral ligand. Carbon monoxide is a neutral ligand. If you look at Cn minus, what type of ligand is this? Is it anionic or neutral? You know the answer.
Anionic.
It is anionic, so it's a Cn minus there. Suppose if I have an amino acid.
Dr. Char, can I ask a question?
Absolutely, anytime, sir.
So you have anionic and neutral. There can't be, so there cannot be cationic ligands.
Can you tell me why cationic ligands are not available? Because you need to have.
There's no lone pair electron, right?
Correct. So cations cannot serve as ligands because you need to have excess electron density for it to combine with a metal. All right. Am I clear here, folks? So now that you know, the next thing is what type of ligands that complexes that you may have. You may have 1 to 2 complexes. That is, you have a metal and 2 ligands around it. An example of this is AzNH3 twice, right? That we talked about. That is a metal and 2 ligands. The other most popular thing is metal with 4 ligands. Metals with 4 ligands can be 2 types. They can be square planar or they can be tetrahedral. Okay. For example, if I take platinum Cl4 2 minus, that is a metal to ligand ratio is 1 to 4, which is what we're talking about. This is a square planar complex where platinum and the 4 chlorines are arranged in a square planar configuration. If you go back, we talked about this not as a coordination complex, but as an example of symmetry. And we said this is a D4H molecule, right? Okay. So in general, if you look at the configuration of platinum here, it's a platinum 2+ in this case. You know the charges, right? Chlorides are anionic ligands. There are 4 chlorides, so 4 negatives. If the overall charge of the complex is 2 minus, then charge of platinum must be 2 plus. And if you look at the electronic configuration of platinum 2 plus, you find that's a D8 configuration. In general, most complexes in which the metal has a D8 configuration, such as nickel 2 plus, palladium 2 plus, platinum 2 plus, these complexes tend to be square planar, because that is how the geometry stabilizes the electronic structure. On the other hand, most complexes of zinc and the main group metals. So for example, if I have PbI4, 2 minus, this is again 1,2,4 ligand, and this one remains as a tetrahedral. So you have the tetrahedra, just like a methane molecule. You have the lead in the middle and the iodines in the corners. So if you have 1 to 4 complexes, usually the geometry could be square planar or tetrahedral. Similarly, if you have extremely bulky ligands, like anthracenes or, with a lot of atoms in the functional group, if the ligand is a bulky functional group, usually tetrahedral geometry is preferred for obvious reasons, right? In a square planar geometry, putting 2 bulky ligands next to each other is not electrostatically more feasible because of the repulsions and the steric hindrances. So one way to minimize that steric hindrance is arranging them in a tetrahedral fashion. So if the ligand is huge, usually they go with tetrahedral configuration. But again, whatever I'm saying, there are exceptions, but these are general observations. Okay. So similarly, the other important class of complexes are octahedral, where you have metal surrounded by 6 ligands. So you have the octahedral geometry, the metal, and the ligands occupy the 6 apex positions of the octahedron. Again, please keep in mind that it is not necessary that all else will be same. Sometimes you can have 2 of one kind, 2 of another kind, and 2 of another kind. So for example, you can have a platinum, 2 chlorines, 2 bromines, and 2 iodines. That is also a complex, still octahedral. Okay, may not be perfect octahedra, but still we can define that as an octahedral geometry. Am I making sense here, folks? Okay, I mean, you have seen that in the video, but I'm not trying to play the video for you because you already have it. You can play it yourself. I'm just giving you other examples that you may not see it in the video. All right, so continuing on. Once we identify the different types of coordination complexes, the next thing is naming a complex. Okay, so I'll start with a complex, and I'll tell you what the rules are. Whatever you do in naming a complex, first thing is you need to identify what the metal is, what is the oxidation state of the metal is, what is the charge on the coordination complex, and how many different types of ligands are possible, right? And finally, you should know the formula of the neutral complex. So, all right, so let's start with a neutral complex, okay? And then we'll talk about cationic complexes and anionic complexes. These are dealt differently. So let's talk about a neutral complex like this. Platinum surrounded by 2 amines. Okay, I think I sent you in the videos where the names change. Ammonia, when you name it as a ligand, is called amine. Chloride is turned into chloro. So ide moves into O when you're naming the complexes. Okay. Sulfate. Whenever you see the ending as E, that E must be replaced by an O. So for example, if I have SO4 2-, all by itself SO4 2- is called sulfate. But if it is a part of a coordination complex, if it acts like a ligand in a complex, its name should be just the last letter E should be changed to O. So we say sulfato. For example, if I have acetate, acetate is the name of this ligand. So when it is a form of a coordination complex, what should its name be?
Is it acetato?
Acetato is absolutely correct. If it's a form of the complex, if it is all by itself, standing free, then we call that acetate. But if it binds to a metal, suddenly its name changes from acetate to acetato. Similarly, if there is nitrite, so this is the free ion, nitrite. If it is a form of a, if it is attached to a metal and forms a complex, how should we call this then?
Doesn't it depend on how it's bonded?
Yes, that is true. We'll talk about that in a minute. But if it is bonded through regular means with nitrogen ending. Nitrite should become nitrito, right? Because the E changes to O. So we say nitrito. Am I making sense here, folks? So this is the thing. I think you have a table of the classical names, that the names that you're familiar with so far, and when they form a ligand or when they act like a ligand in a complex, suddenly the name changes. So you are responsible for memorizing all the names. Although in the exams, of course, I'm not proctoring, so you can always keep a sheet of different names next to you as a reference. All right, so let's talk about neutral complex here. All right, so the first thing is, what is the metal here?
Platinum.
Platinum, okay. If the complex is a cationic complex or a neutral complex, then the name of the metal does not change. We just still call that platinum. And usually the name of the metal comes in the end, not in the beginning. Okay. All right. Now, what is the charge on the platinum here?
Is it +2?
It's +2. Why is it +2?
Because each of the chlorines is -1 and the NH3
There
is
Yes, NH3 is a neutral ligand. There's no contribution to the charge, but the chloride has 2 negative charges. Since the overall complex is 0, neutral, so platinum should be 2+. That oxidation state of platinum +2 must be written right next to the name of the metal. So you need to always find the oxidation state before you start naming the complex. The next thing is,
Hey, Dr. Chari, I'm sorry, I have a question.
yes.
So how come in like the copper complexes, like it's like cuprous and like cupric?
Mhm.
Like does platinum get that? It doesn't get the same like
No,
treatment?
and we will not use those terms us and ik in these coordination complexes.
Oh, for
Now,
all of them, like for,
Trevor, yes.
okay.
What did you say before?
Okay. We don't use that one. It's only in the salts that we use, but I'll explain to you. Maybe I'll take some examples of copper too and start, we'll learn together how to name those complexes. But let's complete this one. When you have a neutral ligand and an anionic ligand, the anionic ligands are named first, followed by neutral ligands. And then we have to tell people how many such anionic ligands are there. So in this case, I have 2. So 2 basically starts with dichloro. This di tells you there are 2 chlorines. And then followed by the neutral ligands. So we have a neutral ligand of ammonia. Ammonia is called amine. So dichlorodimine, platinum 2. So that is the name of this complex. I'm starting with simple examples. We will, of course, go a little deeper because I don't want to start with a complex example and then confuse you. So start with a simple one. Is this clear, folks? Okay. Yes.
I have a quick question. I just want to double check. You put chloro for ahead of the amine because the amine is neutral and the anion goes first, right?
Right. Exactly. Anionic ligands are named first, followed by the neutral ligands. Let's say, is this clear to all of you? One more thing that you have to keep in mind. There are no spaces between dichloro and diamine and platinum. They're all written as one string with no spaces. So it is written as dichloro, diamine, platinum 2, period. Okay. Now let's play a game. Let's say I have a Cl and a Br. So I have 2 anionic ligands now. Which one should be named first?
Bromine.
It's basically alphabetical. So if you have 2 ligands, more than 1 ligand, then you go by alphabetical order. So we say bromo, chloro, diamine, platinum 2. Am I making sense? Is this clear to folks? It's simple. This is the scheme that we use if the complex ion is a cation too. So let's take a couple of examples of that. Let's take CrH2O4, Cl2, and HCl. Okay, so you have some ligands within the coordination sphere, and there are functional groups outside the coordination sphere. These are called counterions. These are called ligands. See, I have chlorine in 2 places. One chlorine is a chloride, and the other one inside the coordination sphere goes by the name chloro. This chloride is basically giving you a charge balance for the complex. So what should be the charge on this entire complex here? If there is 1 chlorine outside, chlorine is -1, so this should be +1. If this is +1, what should be the oxidation state of chromium here? Please keep in mind, water is a neutral ligand, and you have 2 chlorines.
Is it +3?
You are absolutely correct. That's a +3 and 2 minus. That gives you an overall charge of 1 plus. Now we'll start naming them. So how do you name this complex now? Whenever you have a coordination complex with a plus and a minus, just like in normal inorganic compounds, cations are named first, followed by anions, right? When you have NaCl, you don't call that chloride sodium, but you call that sodium chloride because cations are named first. So same thing applies here too. All right, the cation here happens to be a complex ion, but the rules the same. So how do we begin this name then? We have 2 anionic ligands. They should be named first, right? So that should be dichloro. And there are 4 water molecules, tetra,
Aqua.
tetra aqua. Sorry. Tetra aqua,
Chromium 3.
chromium 3, followed by
Fluoride.
chloride. You don't have to say how many chlorides are there. Monochloride is not necessary. All right, so let's name this dichloro tetraamine. You see, everything is written in one line. Tetraamine, chromium 3 chloride. Am I making sense here?
Professor, is it aqua or is it amine?
I'm sorry, what did I say? Amine, aqua. Because
Sorry, I
we're
was
doing
just
too many.
confused.
No. You're not confused. It's me, tetra aqua. Because we were doing a lot of amine examples. It was just going through this overdrive, or what we call hangover. Too many amines. Now, in this example, it is aqua. So dichloro tetra aqua chromium 3 chloride. You also should be able to write the formulas once the names are given to you. Okay. So it goes both ways. Sometimes we ask you what's the correct name of this complex. Sometimes we'll ask you what's the correct formula of the complex. And we'll give you the name of the complex. That's how the exam questions are framed. All right, so the next question is, next question we have is, what happens if the complex ion is an anion? So let me give you an example of this. Let's say if I have Na2 PtCl4. Now, you have the complex ion as a part of an anion. What should be the charge of this complex anion? I have 2 sodium ions here, right? So 2 positives. So for it to be neutral, this net charge on this complex should be 2 minus. If net charge on this complex ion is 2 minus, what should be the oxidation state of platinum here?
+2.
+2, beautiful. That's the first thing that we do before we start naming the complex. Identify the metal, identify whether the complex ion is neutral or anionic or cationic. And third step is to find the oxidation state of the metal. Once that is done, we follow the rules again. Cations first, anions last. So what's the cation here? Sodium, right? Don't say disodium, please. It doesn't matter how many sodiums you have here. You just start with sodium. What should be the name of this one here? We start with the anions, right? Chlorides. So what should we call this? Tetra? chloro, sodium tetrachloro. Here is a small difference. In the case of neutral complexes and cationic complexes, we were writing the full name of the metal with no suffix. But if the complex happens to be an anionic complex, you must end the name of the metal with an ate, A-T-E. Okay, so this is tetrachloroplatinate, ATE, and oxidation state of 2. So let me go back again. Sodium, because that's a cation. In naming the coordination complex, which is the anion here, start with the ligands, tetrachloro. Because it's an anionic ligand, it is sorry, just 1 second. I'm in a class right now. Please don't call. Sorry about that, folks. So let's continue with this. Sodium tetrachloroplatinate, ATE, tells you that it is the anionic ligand. All right, am I clear up to this point? You also have to keep in mind that, let us say, if this were to be copper complex, because somebody was asking me about this, about copper situation. Okay. All right, we'll do the same thing. Luckily, copper forms the same complex such as the platinum here. So that's a 2+ right there. So we say this is sodium tetrachloro. We don't say copper. We use the word cuprum is the Latin name of copper. We use the Latin name and add ate. So it is a cuprate 2. Again, you have to make yourself familiar with the Latin names, because we don't use the conventional colloquial names in naming the complexes. Let's say if I have, instead of copper, lead. What should we name this as? Again, sodium tetrachloro. Should we say leadate? No. We don't use the conventional names. We should always go by the Latin names for this. Anyone knows the Latin name for lead?
Isn't it, I don't know if I'm pronouncing it right. Isn't it plumbate or plumbate?
Plumbum. Plumbum is the, just like plumbing, right? I mean, the name came from the application. Lead in the past used to be used extensively in the piping and plumbing. So that was the plumber's favorite metal. So that's where the name came from. So it's a plumbate. So we say sodium tetrachloro plumbate 2.
Professor, just to make sure, we are adding the 8 because the ATE at the end, because the charge of the complex is -2, right?
You nailed it. That's precisely the reason. If it were to be neutral or cationic, we will not use that 8. 8 is used exclusively in anionic complexes. Am I making sense here, folks? Okay, I'm trying to be slow and at the same time make sure that we all understand the rules here. I'm giving you lots of examples, so you must be familiar with the Latin names, because if you have tungsten, right, we don't use tungsten, because anytime you see the name and the symbol being different, right, then you know the actual symbol must be from a different name. That is the name that we should be using. Tungsten has a formula of W. There is no W in the spelling of tungsten, right? So definitely this must have a different name. Anyone remembers what the name is? It's called wolfram. So wolframate. So we don't say tungstate, but although sometimes people say that, but to be strict, we should always use the word wolframate. Similarly, if it is silver, right? You know, argentate. Argentinium is the Latin name for silver. So when you have a silver complex, we should, if it is an, of course, if it is an anionic complex, then we should use argentate. Am I making sense here, folks? Okay. So keep that in mind. Similarly, mercury complexes, hydroargentate. Hydroarginium is the name for mercury. So that name is from that place. All right, so let's take a couple of more examples before we continue with isomeries. There's so many things to talk about. K3FeCN6. So we have potassium, iron. So what should be the charge of the complex?
Should it be -3?
You're absolutely correct, because there are 3 potassiums. So that should be -3. If that is -3, what should be the oxidation state of iron?
+3.
You're absolutely correct. So what should be the name of the complex then? Going by the example that we did before, there should be potassium. Please don't ever say tripotassium, because for metals and coordination complexes, we don't use those prefixes. Okay, that's just potassium. And there is only one type of ligand, anionic.
Be hexacyano.
We don't say ironate, right? You all know about ferrum, right? Ferrum is the actual Latin name for the iron. So we say this is potassium hexacyano. If it is cyanide, ides go into O. Chloride goes chloro. Bromide goes bromo. Iodide, IDE goes to O. So hexacyanoferrate 3. Let's put another one. If I have K4 FeCN6, what should be the name of this complex? So there are 2 complexes possible with potassium and cyanoferrates. What's the difference between them?
Is the only difference the charge on the iron?
Yes. So if this is what? This should be what? The charge in the complex should be?
Or minus.
Excellent.
So then the iron's only +2.
Iron is +2, yes.
So it's potassium hexacyanoferrate 2.
Absolutely correct. So same thing here. The only difference is instead of ferrate 3 in the previous example, this is now ferrate 2. You see K3 FeCN6, K4 FeCN6. Can I tell you one more thing about these complexes, folks? This complex kills humans in 2 minutes. This is totally innocuous. See how different the properties are. So if you're asking me what's the difference between these complexes, it's the difference between life and death. They look very similar, right? But this guy releases cyanides into the body, bodily fluids, and kills humans very quickly. Not only humans, any life. This guy, in fact, it does not. This is where the critical thinking comes in. So how can we use these complexes? Suppose if somebody is accidentally poisoned by cyanide, and if you want to remove the cyanide as quickly as possible from the blood, what type of iron salt would you give that patient? Iron 3 or iron 2?
Iron 2.
Iron 2 because
If not, you kill him.
this complex is very stable. It binds to the cyanide in the body very quickly. And it is non-toxic. When he got frustrated for some reason, he took the cyanide, but we didn't know. And by the time we knew, she was gone already. But however, if there is an accidental ingestion, if you're working in a lab where you have to deal with cyanides, and if you were in a situation like this, sometimes accidental poisoning can happen. It's not only through oral. If you have any open wounds, the cyanide can go through the open wounds too. So you got to be very careful with these things. So all the labs that you work with cyanides will have ferrous ammonium sulfate solution made next to that. So if you have an accidental poisoning, immediately have to drink a lot of ferrous ammonium sulfate, which is iron 2 plus sulfate solution. I like to tell these things. These are the facts. It's important to know, just not only naming, but what exactly is the difference? Yes, there is a difference in the names, but also the properties are just night and day difference. Just one more potassium, that's all it takes to change the life of it. Okay. All right, so let's do one or two more examples before we continue with this. All right, sometimes you may have a ligand that can bind from using two atoms in the same molecule. For example, if I have NH2, CH2, CH2, NH2, it's called ethylene diamine, right? So there are two amine groups and an ethyl group in the middle. So this is called ethylene diamine. In coordination complexes, we don't write the name as ethylene diamine, but we just use the abbreviation EN. So whenever you see EN as a part of a ligand, what they're talking about is ethylene diamine. All right. Now, what ethylene diamine does is when you have a metal like cobalt 3+, it can use both the nitrogens within the molecule and claw the complex. So these are like the tooth. So in this molecule it has 2 teeth. So we say it's a bidentate. Some molecules have 3, tridentate. Some molecules have 6, hexadentate. Very complex molecules like heme itself is one large molecule that has about 6 nitrogen points. Chlorophyll, same thing. So these are called bidentate complexes. Some are called tridentate depending on how many points of contact they may have. Okay. Now, how do we name complexes that have bidentate ligands? Here is the rule. Follow me carefully. Let's say if I have complex like this, CO, cobalt, EN, which is ethylene diamine, 3 of them, and then we have 3 chlorides. So how do we name this? Now, if you have 3, right, each ethylene diamine gives you 2 points of contact. So this is more like an octahedral complex in which ethylene diamine attacks 2 positions of the octahedra simultaneously. So octahedra has 6 points of contact, right? So using 2 points of contact for each molecule, you can fill the octahedra. So this is an octahedral complex. How do we name this? There is a small thing that we have to learn when we're dealing with examples like this. First of all, we all know this is a cationic complex, right? The charge should be 3+. Because ethylene diamine is a neutral ligand, it's not anionic, it's neutral, just like an amine group. So the cobalt should be 3+2. All right. Now, if you were to name normally, if this were to be a chlorine, then you say trichloro. Right? But here is the name problem. If the name of the ligand, watch me very carefully. If the name of the ligand contains a numbering information, for example, when we call this, what do we call this? Ethylene diamine. That word di gives you a numbering information here. So whenever the name of a ligand contains a numbering information, then you cannot use, tri, tetra, so on and so forth. So here is the rule. So if your ligand, especially if you're ethylene diamine and so on and so forth, we'll give more examples later on. If there are 2 of them, then we don't say diethylene diamine, but we use the word bis. So we say bis-ethylene diamine. That means there are 2 ethylene diamines. If there are 3 of them, we call this tris. And if there are 4 of them, we call this tetrakis. If there are 5, we use pentakis. Okay, so if you go back to this one here now, I have a ligand, a strange ligand that has a numbering information to it. So I will call this tris-ethylene diamine cobalt 3 chloride. So we call this tris, not tri. Tris-ethylene diamine cobalt 3 chloride. Don't say trichloride. Because once you work out the formula, it has to be trichloride. If you have cobalt in 3+ state and you have neutral ligands, so the charge of the coordination sphere should be 3+. So clearly need 3 chlorides to compensate the charge. So there is no point in writing trichlorides, just chlorides. Am I making sense here, folks? Okay. This is a special case when your anion or the ligand has a name that contains some kind of a numbering information. So for example, if you have EDTA, you heard of this, right? EDTA? Those of you who have taken quant must have heard something about what does the EDTA stand for? It can also act like a ligand. Ethylene diamine tetraacetic acid, right?
Is it a solvent?
Yeah, it's a ethylene. It's a complexing agent. It's a ligand. It can use 4 of them. There are 2 carboxylic acid groups and 2 amines, right? The carboxylates can also bind with the metal. So do the amines. So ethylene diamine tetraacetic acid is a very important ligand. So when you have EDTA, you can't use tri-EDTA, no. Because ethylene diamine tetraacetic acid, the words D and T refer to numbering scheme, di and tri. So when you have an EDTA complex, you have to use the prefix tris. Okay, now you get a feeling of when you use the tris, bis, tetrakis, and when you use the normal di, tri, and tetra. It depends on the nature of the ligand. Am I making sense here, folks? Yeah, so I want you to again continue with your lectures there. It's already 12:15 now. I want you to focus your attention. We'll go over the ionization and electron scheme next lecture, the 18 electron scheme. I would like to have the exam around November. I was told by my fellow professors not to bother you guys during the election week because some of you may be actively volunteering and you may be involved. And there may be some stress to some of you. So in our department, we're not giving any quizzes or exams during the November 3rd to 10th, that week. So our exam will be after November 10th. Okay, so most likely between the November 10th and 15th time frame. And that exam will cover coordination complexes. It will cover point group symmetries, and it will also have questions on MO theory, molecular orbital theory. These are the 3 important topics for that exam.
Professor, a really quick question. You said EDTA, we use tris, but it also has di in it. Why don't we use di?
Because in it, remember what I just told you, if the ligand has anything that suggests it has a number, then we don't use mono, di, tri.
Okay.
We have to use tris, bis.
Okay, so why don't we use bis then? Because it has di too.
No, because it depends on how many EDTAs we have. If I have 3,
Oh yeah, that's right. Okay.
then it is tris. If it is 2, you're right, I use bis.
Okay.
It depends on the number of EDTA units attached to the central complex. Does it
Thank
make
you.
sense?
Yes, thank you.
Thanks, Guru. Yeah, keep asking questions. I know, you know, I always get beautiful questions, you know, because sometimes I may not be thinking what you're thinking. And the only way I know what you're thinking is when you ask me a question. Either I correct myself or maybe clarify with a couple of more examples. Otherwise, I tend to think that, oh, you all understood everything. That's sometimes a big mistake teachers make. You know, I teach something and then I say, oh, it must be very clear to all of you because it's clear to me. That may not always be the case. Unless you ask me questions, you know, then I can give you more examples. All right, folks, Well, thank you very much for your time. Again, I'm not trying to repeat what is already loaded in the YouTube videos that I sent you. This is kind of supplements it, it kind of gives you additional information. So now you can go back, and when you watch those lectures, perhaps it makes a little bit more sense now. All right, folks. So see you all next week.
Thank you, Professor.
Thank you.
Thank you very much. Thank you.
Thank
you
you,
all.
Chari.
Thank you.
Yes,
Thank
thank
you,
you.
Hannah. Thank you. Wonderful.